Hello everyone, welcome to Beyond Infinity. Today in this video, we will discuss why satellites don't fall to Earth, the full concept of gravity, the physics behind orbits, real-life logic, relevant mathematics, and thought-provoking related questions. Have you ever looked up at the night sky and wondered, if gravity pulls everything down, then why don't satellites fall back to Earth? After all, gravity is always pulling, right? Today, on Beyond Infinity, we're answering this mystery, not just with facts, but with the logic, math, and magic of physics. Gravity is a force of attraction between two masses. The more mass an object has, the stronger its gravity. That's why Earth's gravity pulls us and everything around it toward its center. But here's the twist. Gravity doesn't always make things crash. Sometimes, it makes them orbit. Imagine throwing a ball. The harder you throw it, the farther it travels before hitting the ground. Now, imagine you're on top of a mountain, and you throw it so fast it falls around the Earth instead of onto it. That's what an orbit is. This was beautifully explained by Isaac Newton in the 1600s with his idea of the cannonball thought experiment. He imagined firing a cannon from a mountain. Fire it fast enough and it will fall forever around the Earth, never hitting the ground. That's orbital motion. Satellites in space are constantly falling, but they're moving forward so fast that as they fall, the Earth's surface curves away beneath them. This perfect balance between the pull of gravity and the satellite's forward speed is called a stable orbit, so satellites are falling, just not down. Let's break down the math. The gravitational force is given by Newton's law. F equals g times the product of m1 and m2 divided by r squared. Where F is the gravitational force, g is the gravitational constant, m1 and m2 are the masses of the two objects, and r is the distance between their centers. To stay in orbit, a satellite needs just the right orbital velocity, which is given by the equation v equals the square root of gm over r, where v is the orbital speed, g is the gravitational constant, m is Earth's mass, and r is the radius from Earth's center. For example, to orbit Earth at about 300 kilometers above the surface, a satellite must move at approximately 7.8 kilometers per second. That's around 28,000 kilometers per hour. But what happens if a satellite slows down? It loses altitude. If it slows too much, it burns up in the atmosphere and crashes. And what if it speeds up too much? It escapes Earth's gravity. This is how we launch probes to the Moon, Mars, and beyond. Some people think satellites are floating, but they're not. They're actually in freefall. They just miss the Earth every second. That's the magic of physics. Even astronauts aboard the ISS feel weightless because they're falling with the station. This is called microgravity. In space, the dance between motion and gravity is delicate and precise. Gravity pulls, speed escapes. But the perfect balance between the two creates orbits, our cosmic racetracks. So next time you look up and see a tiny blinking satellite crossing the night sky, remember, it's not floating, it's falling forever. This is Beyond Infinity. Keep questioning, keep exploring. If you like this video, don't forget to subscribe to this channel and also share it with your friends and fellows.